Okay, so the last part of our electromagnetism is our DC motor. We use electromagnetism concept to apply in real life. Okay, so what is a DC motor? DC motor basically converts our electrical energy to mechanical energy. Yeah, in this case, it's our kinetic energy because DC motor is a kind of rotation, right? Yeah, the coil of wire is rotating inside a magnetic field. It can be found inside our hair dryer and our fans, right? So if you take a look at this diagram, we have a battery. This battery, you know, cause the current to flow, okay, via the carbon brush. This rectangular thingy is the carbon brush. This carbon brush is connected to what we call the split ring commutator. So the circular, semicircular thing is the split ring commutator. Yeah, so the current will flow through the split ring commutator into the coil of wire inside our magnetic field. Alright, so the coil of wire, since there's a current flowing through the coil of wire inside the magnetic field, it will experience a magnetic force. If you use your Fleming left hand rule, your B field pointing towards the left, your current pointing in this particular direction, you will see that your thumb is pointing in the upward direction. Okay, so this particular section of your wire will experience a force in the upward direction. Okay, then of course the current will flow through this particular section. And okay, at this particular section, the wire will not experience any force because remember, in order to experience force, not only that your wire must carry current, it must be perpendicular to your magnetic field. But at this point, right, your current and your magnetic field is parallel. Okay, so this is parallel. Hence, it will not experience any force. Okay, now of course, it will flow through this section. Okay, so this section, if you use your Fleming left hand rule, your direction of force will be pointing in the downward direction. Okay, so it will rotate in the clockwise direction. Okay, and the purpose of your split ring commutator is actually to reverse the direction of your current so that it will continue rotating in the clockwise direction, right? Okay, all right, so carbon brush is connected to a battery so that current can flow to the coil via the commutator. Okay, so this split ring commutator comprises of two half ring that allow the direction of current to reverse every half a revolution in the coil. Why is the reversal of current important? Because I want the coil to keep on turning in the same particular direction, right? Okay, so let's go to this diagram. Okay, so you look at diagram A. So we have a battery that is connected to the carbon brush and your split ring commutator. This current will flow to this commutator, then flow through the coil, right? So the current will flow from M to N. Okay, and there's a magnetic field pointing from left to right. Okay, if you use your Fleming left hand rule, you'll notice that your thumb, the direction of your force is downward direction. Okay, and the current will continue flowing from K to L. Okay, and you use your Fleming left hand rule, the direction of your force is upward, so it will rotate in the clockwise direction. Okay, after rotating, okay, it will go to the orientation B, orientation C. Okay, then next we will look at diagram D. Okay, so diagram D, the coil has rotate in this particular orientation. Okay, where your MN is on the opposite side now. Okay, and your LK is in the opposite side as compared to your diagram A. Okay, so for the battery, the positive terminal is still right here. Okay, then the current will flow, right? Then okay, so you notice that the current is flowing from L to K now, and the current will keep on flowing from N to M. Okay, if you compare diagram A and diagram B, For diagram A, your MN, the current is flowing in this direction, right? So this is the current. Okay, but for diagram D, your current is flowing in this particular direction. Okay, so you notice there's a reversal of your current in the same wire, MN. And the direction of the force on your MN is downward. Now, the direction of your force is upward. Okay, so this is due to the reversal of your current. If you reverse your current, your direction of your force will become opposite. Okay, so just now it's downwards, now it's upwards. Likewise for your LK. Okay, if you look at diagram A, the direction of the current is flowing from K to L. Okay, so this is K to L. So this is for LK. But now your LK, the current is flowing. Okay, is flowing from L to K. Okay, so this is also the reversal of your current. Okay, so for the force, same thing. Just now is upward, now is downward. Okay, so the reversal of the current is caused by the split ring commutator. Yeah, so that it will continue to rotate in the same direction. Right? Okay, if you do not have the reversal of your current, okay, so let's just say I compare diagram A. Okay, so diagram A, the current in MN is flowing right in this red color, right? So if I put the direction of current as the same, so it's flowing in this direction, current, okay, and KL I put in this form. Okay, so current. Okay, so what you notice is that after rotating and I do not reverse my current. Okay, if you use a Fleming left hand rule, you determine what is the direction of your force acting on your wire MN. Okay, so if you use correctly, you should experience a downward force on your MN and a upward force LK. Okay, yeah, all right. So so you experience these two particular forces, and this is in the anti-clockwise direction. Okay, anti-clockwise direction. Yeah, so just now in diagram A, I want the coil to rotate in the clockwise direction, right? Now if I do not reverse the current, it will rotate in the anti-clockwise direction. So you can see that the thing will not rotate in the same direction anymore. Alright, okay, yeah. So that's why it's very important to reverse your current direction. Okay, next thing is, how do I increase the speed of rotation? I want the coil to rotate even faster. So first of all, I can increase the current. Okay, second of all, I increase the number of turns in the coil. Okay, of course, last but not least, I can place a soft iron core in the coil to increase the magnetic field. Okay, yeah, so let us take a look at this simulation, right? Okay, so if you look at this simulation, right? Okay, let me just run. Okay, so there's one particular section that I didn't mention, is that there's a point where the current will not flow inside the coil of wire. This is when the split ring commutator is not connected to the coil of wire. Okay, so let's see. Okay, so this is the point where there's no current flowing through, but the coil will still turn until it become connected to the split ring commutator again, because of Newton's first law, the inertia, right? Yeah, so imagine you're pushing a toy car, then suddenly you release your hand, but the car still move, although you are not touching it anymore. Because of inertia, it will not stop suddenly, it will still move a bit. Likewise for your coil of wire. Okay, so it will continue rotate. Yeah, okay, so I can increase the speed of rotation by increasing the magnetic field. Okay, so you can see that the speed increases, or I can increase the number of loop. So just now it's just one loop, right? Now it has many loop. Okay, or I can increase the amount of current flow in the coil. So you can hence increase the speed of rotation. Alright, so this is for your